In this section, we will be looking at integration by substitution, which is definitely one of the more challenging topics that we will have discussed in calculus. Integration by substitution is basically the opposite of the chain rule. So remember back in chapter 3, we talked about the chain rule for differentiation. So let's say that the original function that we had was, let's say, 3x squared plus 7 raised to the power of 5. Remember, if I wanted to take the derivative of this, I would have used the chain rule. So we would have said 5 times 3x squared plus 7, so we write the inside function as is, reduce the power by 1, then we always multiply by the derivative of the inside. So what we want to think about is how would I go backwards if I gave you the derivative here and asked you to go back to the original function. This would be a little bit more challenging than the previous problems we've done. We actually have a product. We have 6x times this, and so we have to repackage this product kind of back into the chain rule. So one of the ways that we do that is by thinking about what the inside function is, right? So we have the inside function raised to the power of 4. And then we have, remember, we always multiply by the derivative of the inside function. So what we start to do to repackage is we look at what's outside of that parentheses raised to the higher power. And we have the 6x, and we want to say, well, if this is the derivative of the inside function, then how can I repackage it so that I get back to the original function, right? So you'd have to do some sort of what we call substitution in order to make this integration a whole lot simpler. So the whole point of this whole section is to repackage the derivative, repackage the integrand so that it's a lot easier to see what the integration would be. Integration by substitution actually allows us to complicate more complicated functions, and it's related to the chain rule for finding derivatives. So it's basically the opposite of the chain rule for finding derivatives. Okay, so the key here is all going to lay in step 1. Okay, step 1, we're going to do what we call u-substitution. We're going to let u represent the most complicated part of the integrand. So what's the clue for that? So here's the hint. This is often a function that is being raised to a higher power. So I'm looking for something maybe that looks like this. Something in the parentheses that's being raised to a higher power. Or I'm looking for e to some power. Okay, so we're going to let u represent what's either inside of the parentheses, or we're going to let u represent what the exponent of e is. So these are the two kind of hints as to what to let be u. Once you have your u, then everything else basically follows naturally from what we let be u. Okay, so step 1 is really important. All right. So let's scroll down. So in our first problem, first thing you want to do is you want to let something be u. So we're going to substitute something in place of u. So we're going to look for, once again, our hint was to look for a group of terms in the parentheses that's being raised to a higher power. So everything in here is being raised to a higher power. So I'm going to let u be equal to 2x plus 1. So what we're trying to do, our goal here is to repackage this to be in terms of only u. Okay? Right now we have this variable x floating around. We want this to be only in terms of u. So we've done part of this. 2x squared plus 1 to the power of 7. What we have so far then is u to the power of 7. Now, the rest of the problem is trying to figure out what do we do with the extra stuff that's floating around. What do I do with this 4x and this 2x, this dx that are being multiplied in? Remember, the dx tells me I'm integrating with respect to x, but I still need to somehow figure out what to do with that. How do I repackage that so that I don't have any x's in my integrand? So the next step is to find the derivative of u. So we're going to say du equals. So we're just going to find the derivative of u. So the derivative of u equals, well, what's the derivative of 2x squared? Well, that's 4x. The derivative of 1 is 0. And then we just found the derivative of that with respect to x. So we're going to include the dx here. Now that's really nice, because we want the right-hand side to be equal to all the extra stuff that we have floating around. And it does. 4x dx, those two things multiply together, we have them right here. So we're going to replace everything that's in the green there floating around with its equivalent on the left. We're going to replace that with du. Alright, so we've accomplished our first goal. We let something be u, right, the most complicated part of the expression, and all the extra stuff that's floating around now is also in terms of u. It's du. So now what we're going to do is we're going to integrate u to the 7th power with respect to u. Okay, so now this part's straightforward. So I'm going to add 1 to the power, and then I'm going to divide by the new power. And remember that once we integrate, the du and the integration symbol go away. But we don't want to forget our constant of integration. So the last thing that we do once we integrate u is we go back to x. So we're going to let u go back to what u represents in terms of x. Now when we divide by 8, I'm going to go ahead and just write that as 1/8 times. I think it looks a little bit nicer. So I'm going to represent what u is equal to with the original expression 2x squared plus 1. This right here is our final answer. Now, let's remember something. We can always check our integrand. We can always check our integration. How can I check it? What we're saying is that this is the original function. If I take the derivative of it, I get 4x squared times 2x squared plus 1 to the 7th power. So let's check. Let's take the derivative of this. Okay, so what's the derivative of this? Let's call this our function f, so this is be our derivative of f. So this is the chain rule. So we would take 8 and multiply it times 1/8, and that would give us 1. We would write down the inside function exactly as is. We would reduce the power by 1, and then we would multiply by the derivative of the inside function, which is 4x. Does this look familiar? Yes, this is the integrand that we started with. So remember what we're saying is if this is the derivative, then this must have been the original function. So that if I take the derivative of it, I get back to the integrand. Alright, in example 2, we're going to do a u-substitution again. We're going to let u represent the most complicated part of the expression. So first step is to decide what does u represent. Alright, well, when I look into the integrand, do you see a group of terms in the parentheses raised to a higher power? Okay, once you find that, then that's really easy. We're just going to let that be u. So I'm going to let u equal x cubed plus 2x. So everything that's in the parentheses there. Alright, so here's what we have so far. We have u squared in the denominator. Okay, now we want to write this all in terms of u. So we have all this extra stuff floating around. We have 3x squared plus 2 times dx. And somehow I have to repackage all of that to be only in terms of u. So how are we going to do that? So the second thing is to determine what is du. So what is the derivative of what's in step 1 there? We'll take the derivative of that when you get 3x squared plus 2. And we just found the derivative of that with respect to x. Does that right-hand side look familiar? Yeah, all of this looks like the extra stuff that we have floating around. So what are we going to replace all that extra stuff we have floating around? We're going to replace that with du. So I'm going to write du right here. Now, the top of our fraction looks like it's empty, so I'm going to put a 1 there. And now we are going to rewrite this as u to the negative 2 power. And now we're going to integrate that. All right, we're going to add 1 to the power. Divide by the new power. Don't forget our constant of integration. So the third step there is to actually integrate. Okay, and the last step is we want to go back to x. So the last thing I'm going to do is I'm going to take the u, I'm going to copy everything around it except for u, and then what I have in place of u, I'm going to go back to what it represents. It represents x cubed plus 2x. Alright, and this is our final answer. Okay, they look a little bit more complicated than they actually are if you just go step by step and use the hint for what u should be. All right? So for example 3, it looks really crazy. But the first step is to figure out what should you let be u. Okay, so that's our first step. Take it piece by piece. Well, what we're looking for is a group of terms that's raised to a higher power. So we're looking for something that's in the parentheses raised to a higher power. So it looks like we have e to the x plus e to the negative x. So as soon as I find that, I'm going to write u equals e to the x plus e to the negative x. Okay, so what do I have so far in my repackaging? Then now I have u to the 3/2 power. Okay, what's the extra stuff that still has x in it that hasn't been accounted for? That's all of that stuff there. So somehow we need to repackage that to be in terms of u. So our second step is to take the derivative of what's above. So the derivative of e to the x is e to the x. The derivative of e to the negative x is e to the negative x, but then we multiply by the derivative of that exponent, which is -1. So we actually get e to the x minus e to the negative x power. Remember all of this with respect to x. We'll put dx. Okay, does this look familiar? Yes. This looks exactly like all that extra stuff that we had floating around. So once the right-hand side there matches the extra stuff that we have floating around, we're going to replace all of that extra stuff with du. Now I'm going to put a 1 on the top of my fraction just so I don't have an empty top. But I'm going to rewrite this as u in the top of the fraction, so I'm going to write that as a -3/2 exponent. And now I'm going to integrate. So the third step is once you have everything in terms of u, we want to actually integrate. So we're going to add 1 to the power, which means I'm adding 2 over 2, which gives me a -1/2. We're going to divide by the new exponent, -1/2. Alright, and I'm going to rewrite this to look a little nicer. I'm going to take the -1/2 and I'm going to multiply by the reciprocal of that, so that becomes -2 over 1. And the last thing I want to do is include my constant of integration. Alright, so we have integrated. So what's the last thing we want to do before we leave out? Before I leave out, I want to replace what u represents. So now we have -2 times u to the -1/2 power plus c, and I'm going to take what u represents and I'm going to put it back in place of u in my final answer. So we have -2 times, in parentheses, e to the x plus e to the negative x, all of that raised to the -1/2 power plus c, and that represents our final answer. Alright, for example 4, we talked about when we were integrating or taking the derivative, anytime that we're doing either of those things, anytime that we see a radical, we're going to rewrite that as an exponent. So I have a square root of x cubed minus 1. I'm going to replace that with x cubed minus 1 to the 1/2 power. Alright, so we're going to rewrite that. Okay, as soon as we do that, we're going to use substitution. So we want to know what should we let be u. So you have 2 questions to ask yourself, and the first question is always, do I see a group of terms in the parentheses raised to a higher power? And the answer is yes. Okay, so we have that. So we're going to let that be u. Alright. So let's just kind of take a peek at what we have so far. We have u to the 1/2 power in the denominator there. What's the extra stuff that we have floating around that we want to replace with only things in terms of u? Well, that's x squared times dx. So where are we going to find that information? We're going to find it from taking the derivative of u. So we're going to take the derivative of what we found in step 1. So we have u, we're going to take the derivative of u. X cubed, we know that that would be 3x squared. -1, the derivative of that would be 0, so we won't put plus 0. And then of course we just took the derivative with respect to x. So here's where things start to get interesting. Does the right-hand side look like the extra stuff that we have floating around? Well, it looks really close, but it's not quite the same. For my integrand, I have x squared times dx, but on the right-hand side, I have 3x squared dx, so I don't have a 3 in my integrand, so I can't just put du, okay, because that's not equivalent to what I have the extra stuff floating around. Well, how can I make the right-hand side look like the extra stuff that I have floating around? Well, if I just could get rid of that 3. So that's what we're going to do. We're going to get rid of that 3. I'm going to divide by 3 on both sides. Okay, it's important that we do it to both sides because we have an equation. And that's the same thing as 1/3 du is equal to, the 3's cancel, x squared dx. So if the right-hand side does not look exactly like the extra stuff that we have floating around, then we can divide or multiply something on both sides of that equation to make it look like the extra stuff that we have floating around. Alright, so now we can replace all of that with 1/3 du. Okay, so now we're going to replace all that extra stuff with its equivalent, 1/3 du. Now it looks like our fraction has an empty numerator, so we're going to go ahead and put a 1 there. And I'm going to rewrite this before I integrate. We have a constant multiple of 1/3, and I'm going to bring that outside of my integration symbol. I'm going to bring u to the top of that fraction, so I'm going to write that as u to the negative 1/2 power, and then I'm going to have my du. So this is now a straightforward integration. I'm going to add 1 to the power. So it's adding 2 over 2, so we get u to the 1/2 power, divide by the new exponent, and then I'm going to multiply by 1/3. Don't forget my constant of integration. Okay, the last thing we want to do is we want to replace u with what it originally represented in terms of x. Before I do that, I'm going to rewrite the denominator here. I'm going to multiply by the reciprocal just to make this look a little bit nicer. So I'm going to multiply by 2 over 1. So finally this gives me 2/3 times u to the 1/2 power plus c. And what is u? U is represented by x cubed minus 1. So this is my final answer for example 4. Alright, example 5 brings us to kind of the second type of integration by substitution that we would see. We said that the second type would be letting u represent the exponent of e. So here I have e to the 2x power, so I'm going to let u represent the exponent of e. So that's the second type of substitution that we want to look for. So then what I have then is e to the u, because I'm going to let 2x represent u. What's the extra stuff that I have floating around in terms of x? Well, that's dx. So how am I going to replace that? Well, the second step is to take the derivative of what's in step 1. So I'm going to take the derivative of both sides. So u, the derivative of that is du. 2x, the derivative of that would be 2 dx. So we're taking the derivative with respect to x, so 2 dx. Alright, well, does the right-hand side look exactly like what I've circled as the extra stuff floating around? And the answer is no. But it looks really close, doesn't it? So how do I get rid of the 2? Well, I'm going to divide both sides by 2, and that gives me 1/2 du is equal to dx. So here's the extra stuff that I have floating around in terms of x, and I'm going to replace that with 1/2 du. Alright, so I'm going to say that's 1/2 du. Alright, now I'm going to rewrite this before I integrate, or bring the 1/2 out. So now I'm just integrating e to the u du. Remember, that's really easy to integrate. The antiderivative of e to the u is e to the u. We'll bring down that constant multiple, and we'll add in our constant of integration. And the last thing that we're going to do is we're going to replace u with what u represents, 2x. Alright, so our final answer, let's rewrite a little bit nicer. 1/2 times e to the 2x power plus c. Alright, in example 6, we're going to start out by figuring out what are we going to let be u. So do we have a function inside of parentheses raised to a higher power? Okay, it looks like yes we do. We have ln of x, or natural log of x. So we're going to let u represent natural log of x. All right, so let's just kind of start doing a little bit of replacement. So now we have u cubed. What is the extra stuff that we have floating around? Well, it's x dx. And I'm just going to do something really quick. I'm going to rewrite this. Okay. Notice that x is in the denominator. So if you want to, you could bring that up to the numerator. That would be x to the negative 1 power dx. So let's write it like that. Okay. All right. Well, this is still the extra stuff that we have floating around that we want to replace. Okay. Keep in mind that I want everything here to be only in terms of u. We don't want any x's floating around. So how do I get rid of that? Well, let's go to step 2, and we're going to take the derivative of u. So what's the derivative of natural log of x? Well, that's 1 over x dx. Does that look familiar? Yeah, because 1 over x, remember, is the same thing as x to the negative 1 power dx. So does the right-hand side look like the extra stuff that we have floating around? Yes, it does. So we're going to replace that extra stuff with u. So here's what we have. We have u to the 3rd power. We're going to replace all of that with just u. Okay, so now this is a pretty straightforward integration. We're going to add 1 to the power, divide by the new power, and then we're going to add in our constant of integration. So remember, the 3rd step is to integrate. So I'm going to write this as 1/4 u to the 4th plus c. And the last step is to go back to writing everything in terms of x. So what do we have? We have 1/4 u to the 4th plus c. And what does u represent? U represents natural log of x. So 1/4 of natural log of x raised to the power of 4 plus that constant of integration. All right, example 7 is going to be pretty similar. We want to let u represent the most complicated part of the expression. So the most complicated thing I see is ln of x, or natural log of x. So I'm going to let what's in the parentheses here represent u. Okay, so let's kind of do a little bit of repackaging. So keep in mind, like what we said here, is that ln of x now is in my denominator, so that's u. And we have 1 over x, so we have x in the denominator, right? If we want to, we can rewrite this and bring that x up to the numerator. So that would be x to the negative 1 power, and then we have that dx. Remember, this is the extra stuff in terms of x that we want to replace. So our goal is to replace this to be only in terms of u. So how do we come up with that part? So we said the second step then to replace all of that would be to take the derivative of u. We know that would be 1 over x. We're finding the derivative with respect to x here, so I'll write dx. And that's really the same thing as x to the negative 1 dx. So the right-hand side looks exactly like the extra stuff that we want to replace, and we want to replace it with the left-hand side du. Okay, so I'm going to replace all of that with du. And we'll put a 1 on top of our fraction just so that it doesn't look empty. Okay, so how does 1 over x or 1 over u integrate? Okay, well, if we think back to chapter 5, 1 over u or 1 over x, the integration of that, or the antiderivative of that, would be ln of u. And then we'll add in our constant of integration. All right, so here's the antiderivative. So we've integrated. The last thing to do is to go back to everything being in terms of x. So you have ln of u plus c. What does u represent? U represents ln of x. So we have kind of a nested ln function, which is perfectly fine. Nothing wrong with that at all. All right, so the last two are pretty interesting. Example 8, okay, it looks really complicated, but remember, you want to take it step by step. You want to think, what am I going to let be equal to u? Remember, there's two things you're on the lookout for. A group of terms in parentheses raised to a higher power, or the exponent of e. So it looks like we have e to some power, so we're going to let this right here represent u. So we're going to take the exponent of e, and we're going to let that be our u. Okay, so what do we have so far? Well, we have e to the u power. What's the extra stuff that we have floating around? That's x cubed dx. So we know we want to replace all of that with something in terms of u. So second step, let's find the derivative of u. The derivative of u would be 4x cubed for the first term. The second term would be plus 0, so we won't write that, but we did find the derivative with respect to x, so we'll put our dx. Does this look like the stuff that I want to replace? Looks really, really close. The right-hand side looks almost exactly like the stuff I want to replace, except the right-hand side has a 4 that the original problem did not have. So how do I get rid of it? Well, we're going to divide both sides of this equation by 4. So we get 1/4 du, x cubed dx, and now all of this stuff looks like the stuff I want to replace. So I'm going to replace it with 1/4 du. So I'm going to go ahead and put the 1/4 outside, and we'll put the du inside, and now we will actually integrate. Alright, so really simple integration. Remember, the antiderivative of e to the u is just e to the u. We'll bring down that constant multiple that we brought out. We'll add in our constant of integration. So we said the last thing that we want to do is go back to x. So what does u represent? U actually represents the exponent x to the 4th plus 1. And so this represents our final answer. Okay, and example 9 is going to give us a little hint, and we're going to take that hint and we're going to run with it. And WebAssign also gives you this hint, so when you're working on this problem in WebAssign, just take the hint and run with it. It says that what we actually are looking to integrate is actually simpler if we think about it as 1 minus 4 over t plus 4. So we're just going to take that hint and we're going to say, okay, and we're going to run with it. So we're going to say, here's what we're going to integrate. Okay, now we're integrating with respect to t. Okay, we have two separate terms now, so it's a lot easier to think about it as two separate terms to integrate. So we're going to write the one, we're going to give it its own integration symbol and its own dt. And then this will also give its own integration symbol and its own dt. All right. Okay, so the first integration does not need a u-substitution, so let's just go ahead and integrate that. There's a constant, just 1. Okay, I'm integrating with respect to t, so the answer for that would just be multiplied by the derivative, or sorry, multiplied by the variable that we're finding the derivative of, so we're multiplied by t. Okay, so we're integrating with respect to t, so we're just, remember we have a constant, we just multiply by the variable that we're using in the integration. So that's just t. How can I test that? Well, what's the derivative of t? It's 1, so we're good to go. Minus. Now, this part we're going to spend a little bit more time working with the integration. First of all, this 4 is just multiplied in. Let's bring that 4 out as a multiple of integration outside of it. So that leaves me with 1 over t plus 4 dt. Alright, so we're going to use u-substitution on the second part. What's the most complicated part of the entire expression? Pretty easy. T plus 4. What's the derivative of that? Pretty easy again. That's 1 dt. So let's rewrite what we have so far. So bring down this part. Okay, so we let u be t plus 4, so that's u. dt is the only extra stuff that we have floating around, and what's really nice here is that dt is exactly equivalent to du. So instead of writing dt, I can just replace that with du. So it's a really easy substitution. So I get t minus 4. We're going to integrate 1 over u, which we said was ln of u. Add in our constant of integration. And now the last thing that I'm going to do is I'm going to write everything in terms of t. So we're going to replace u with t plus 4. Alright, so the key for these is to go back to step 1 and to say, what should I let be u? Okay, it's the most complicated part of the expression. We're looking for a group of terms raised to a higher power, or we're looking for, like we did in example 8, the exponent of e. Once you have that, we can find du, and we should be able to replace all the extra stuff in terms of du. Once everything in our integrand is in terms of u, we integrate. Should be a pretty simple integration, and then we go back to what u represents.